week we have Mengdi. Mengdi is a fifth-year PhD student at CMU, supervised by Professor Ding Zhao. Her research aims to build learning-based generalist robots that can reliably interact with the real world. Mengdi has spent wonderful summers interning at Google DeepMind, MIT, IBM Watson AI Lab, and Toyota Research Institute. She holds a master's in ML from CMU and a master's in robotics from Johns Hopkins, and a dual bachelor's degrees in vehicle engineering and management from Tsinghua University. Today she'll be talking about building adaptable generous robots. Maybe you can take it away.
Yeah, thanks Albert for the introduction. And thanks for inviting me. And hopefully we'll find something interesting in the talk. So in this talk, I'm going to talk about my previous research on building adaptable generalist robots. In other words, I want to make the robot being able to generalize to some new tasks, and those new tasks may have new states, new dynamics, or the robot may even have to operate in a totally new environment. And generalization is becoming a really hot topic recently. The reason is that the real world is highly unstructured, meaning that there may be like infinite possible number of tasks in the real world for the robot to solve. And if we take a probabilistic point of view, we can represent the training tasks with a training distribution. And similarly, we can represent all the real world tasks with this deployment distribution. And generally, the deployment distribution can be a really flat distribution, meaning that there are like a lot of possible tasks that are going to happen in the real world. And also, the deployment distribution can be a long-tailed distribution, meaning that there are some critical events that may happen in the real world. However, the probability of sampling those critical events is really small. And there are a lot of like examples showing the training and deployment gaps. For instance, in the household robot scenario, the robot may have to operate some new objects that are not in their training set. And similarly, in the rescue robot scenario, the robot may have to navigate in some really scattered scenarios which are hard to simulate in the training phase. And even moreover, in some human-robot interaction scenarios, the robot may have to closely interact with humans. So in such cases, the robot have to infer the human's latent intent and then generate their actions, and which we already know are pretty hard tasks. So those training and deployment gaps makes generalization a really key property for the robot to be able to be deployed in the real world. And the existing research are trying to evaluate the generalization capability of robots by measuring the algorithm's efficiency and effectiveness, meaning that we want to have the robot being able to like quickly generalize to those unseen tasks and also with high performance. However, I want to argue that there are a lot of other metrics which we may need to consider during the generalization phase. For instance, we may need to consider the robustness and also the safety during the generalization phase, meaning that we don't want the robot to cause any like catastrophic failures during the generalization. And we see a lot of exciting works going on for improving the generalization capability of robots. For instance, there's a surge of interest in like building large foundation models, and we see that the latest RT2X model already have like 55 billion of parameters, which is like pretty large. And to train such large foundation model, researchers are also trying to collect large-scale robot data. For instance, OpenX embodiment dataset has like 22 embodiments, 500 skills, and 60 datasets. And besides collecting data in the real world, there are also other efforts are trying to build more and more realistic simulators. For instance, this like Unisim effort is trying to learn the simulator from realistic images. And we can see that such methods, they actually share the similar idea, which is they're trying to improve the generalization capability during the pre-training phase. In other words, they treat the generalization capability as an emergent capability after we let the robot foundation model be large enough and after we feeding large enough data to the robot foundation model. However, the fact is that the real world will present additional challenges. For instance, the pre-trained robot agent may eventually have to like control some new robots with different morphology, and also even have to operate in like new environment. And moreover, the real world has a lot of uncertainties. For instance, the physical properties of different objects are unknown to the pre-trained agent. And also in some human-robot interaction scenarios, the human's latent intent are also like unknown or unrevealed to the robot. So to handle such real-world challenges, including some unseen tasks or tasks with uncertainties, my research are trying to like build adaptable generalist robots. In other words, I want to make the robot being able to leverage on the prior knowledge it obtained from the training phase and achieve adaptation with to those challenging tasks with high efficiency and also robustness. So in this talk, I'm going to mainly talk about three parts of my previous research centered around like building adaptable generalist robots under different types of supervisions. And when there are demonstrations available in the unseen task, we proposed transformer-based agents to leverage those demonstrations to like achieve like few-shot generalization to those unseen tasks. And when the demonstrations are not available, meaning that we only have the rewards in the unseen task to help the agent achieve the adaptation, in such situation, we propose to boost the generalization capability by automatically discovering the relationships between the new task and also all the already seen tasks to improve the generalization capability. And the last part is heavily motivated by the recent success of the large foundation models. And we, for the first time, proposed the robot tool system, which enables the creative robot tool use behaviors to solve multiple like physical puzzles in a zero-shot manner. So let's start with the first part, which is building transformer agents to solve some learning from few-shot demonstration problems. So the key observation we have in this line of work is that we notice the learning from few-shot demonstration problem in the robotics domain is closely related to the in-context learning paradigm in the originally proposed in the natural language processing domain. So basically, the few-shot robot learning requires the human experimenters provide a few demonstrations to the robot, and those demonstrations are definitely demonstrations for the unseen task at the deployment time. And the good news is that we indeed can collect such demonstrations, although those demonstrations may be really limited. For instance, we can have the human user to directly control the robot and collect demonstrations in the robot's configuration space. And moreover, we may also be able to get some human play data on the internet to help to serve as a demonstration to help the robot achieve adaptation. And in-context learning in the NLP field is basically saying that the user will need to provide a few prompts to the large transformer models at the inference time. And we know that in-context learning is the key that enables the few-shot and also even the zero-shot learning capability of the large transformer models. So our question becomes, can we enable such like few-shot, even zero-shot learning capability in the robotics domain by leveraging on the power of the large transformer model? So in our work, we propose the prompt decision transformer, which basically casts the learning from demonstration problem to an in-context learning problem. And the inference pipeline is like this. So the prompt decision transformer will first sample a short trajectory prompt from the demonstration dataset. And such a trajectory prompt is really short. It may only contain like 2 to 15 time steps in the demonstration. And the prompt decision transformer will condition on both the trajectory prompt and also the recent context as input, and then like auto-regressively generate the actions. And here I also want to show some detailed architecture of our prompt decision transformer. Basically, we can see that the representation or the format of the prompt and also the recent context are the same, which are actually sequences of tuples, and each tuple will contain information in one time step, and each tuple actually contains the reward to go, the state, and also the action. And I want to mention that such format is the same as the original format proposed in the decision transformer paper, but the difference is that we have this prompt augmentation to achieve like few-shot generalization to the new task. And through experiments, we indeed find that prompt decision transformer can generalize to new goals. Like for instance, in this cheetah velocity environment, if we train in the training phase, we have like 45 tasks, and each task have like different goal velocity. And in the testing time, the prompt decision transformer is tasked with like 5 new tasks, and each task will have like new goal velocity. And the benefit of the prompt decision transformers architecture is that it doesn't require gradient updates to solve those unseen tasks, and we only need to do the forward inference to solve those unseen tasks. And the most important finding in our prompt decision transformer paper is that we find the prompt decision transformer leveraging on the in-context learning paradigm, it performs better than the few-shot gradient-based fine-tuning methods. For instance, in this pick and place environment where different tasks have different target goal location, we notice that prompt decision transformer have better asymptotic performance when compared with other baselines. And also when comparing with the SOTA baseline at that time, which is back in 2021, we noticed that our prompt decision transformer can actually achieve 6 times faster improvement when compared with the SOTA baseline. So those observations actually help us draw the conclusion, which is the in-context learning paradigm, at least in the classic meta reinforcement learning setting, outperforms few-shot gradient-based fine-tuning and also the SOTA offline meta reinforcement learning algorithm. And the main reason we think is that the prompt decision transformer can actually successfully extract the goal information provided in the prompt. And here are some realizations of the trained agent. For instance, like we see that the prompt decision transformer can pick the object and place the object in different target locations across different episodes. And we also notice that prompt decision transformer is strong in both interpolation generalization and also like extrapolation generalization. And in the end direction environment, the interpolation generalization means that we will sample the target goal locations in the unseen task, which is within the ranges for sampling the goal directions for the training tasks. And the extrapolation generalization, meaning that we'll sample the goal target directions out of the training ranges for the training tasks. And we notice that in such setting, prompt decision transformer can actually perform really strong interpolation generalization and also extrapolation generalization. And it also outperforms the SOTA offline reinforcement learning baseline by a really large margin. And however, although we see some nice results from the prompt decision transformer paper, however, we notice that there are a lot of limitations. One limitation is that the prompt decision transformer can only, in our setting, it can only generalize within environment, meaning that if we train in this cheetah velocity environment, we can also generalize to like new tasks also in this cheetah environment. In the future, we definitely want to have like stronger generalization capability, meaning that we may want to have like the robot agent solve tasks with new objects or even in new environment. And we see a lot of like interesting works in building robot foundation models by scaling up the model's parameters and feeding the model with large number of data. And although we see those models have really strong multitask learning capabilities, recall that eventually after we deploy the robot agent in the real world, the robot may have to solve some new tasks which are out of their training distribution. So in such situation, we have to adapt those robot foundation models. However, the millions to billions of parameters in those robot foundation model will make the adaptation non-trivial, meaning that if we simply update all the parameters in the model, it may consume a lot of like computation resource. So then our question becomes, can we adapt those large robot foundation models in a relatively data and parameter efficient manner? So in our following up work, we propose the hybrid decision transformer. Yeah.
Yeah. Do you mind
Is
if I
there
ask
any
a question?
Sure, yeah, please.
Yeah. Actually, I was hoping, can you go back to slide 11 for a second? And I was hoping you could tell me at least a little bit more about the distributions of data that you collect during training for in-context learning. Because this is always a really delicate thing to figure out, even for most meta learning.
Yeah,
If you
so
have to collect trajectories, what is the distribution and proportion of trajectories you need to collect from training to test?
yeah, so basically in this setting, we also have 45 tasks for training and 5 tasks for testing. And in this and direction environment, the 45 tasks have like different goal directions, meaning that we have a range for sampling the goal direction for all the training tasks. And the interpolation means that we'll, for the testing task, we'll sample the goal direction within the training range. And extrapolation meaning that we will sample the goal direction out of the training range. So it's like, did I answer the question? Is that clear?
Yeah, and then you're providing one of these trajectories as the in-context learning to decide where the goal direction would be.
So the demonstration is you can think of the demonstration as the rollout trajectory, meaning that if you're trying to roll out the prompt decision transformer to solve some unseen task, we'll first assume that we have a demonstration in such unseen task. And the demonstration will contain the states of the ant agent at different time steps. So we'll like we'll first sample a short segment from such demonstration, serving as the prompt, and the prompt decision transformer will leverage on such prompt to do the rollout.
Okay. All right. Yeah. Thank you. Is there other questions? No? All right. You can keep going.
Great.
Thank you.
Yeah. So recall that the motivation of the hybrid decision transformer is we are trying to have some like efficient adaptation mechanism to help the robot foundation model, which have a large number of parameters to adapt to some unseen tasks. And hybrid decision transformers input is it's actually the same as the ones we use in the prompt decision transformer, which include both the trajectory prompt and also the reason context. And the different part is that the hybrid decision transformer will use a hypernetwork to process the trajectory prompt, and then the hypernetwork will generate the parameters in the adapter, and the adapter are injected into different transformer blocks. And hybrid decision transformer have several nice features. The first one is that it is parameter efficient. And by having this adapter, by making this adapter having the bottleneck architecture, we can reduce the adapter's parameters. And in result, the adapter's parameters may only occupy 0.5% of the whole model's parameters. And in the adaptation phase, we only need to adapt the adapter's parameters, so it may largely reduce the computation resource. And the second nice feature is that because we only the hybrid decision transformer doesn't suffer from the catastrophic forgetting problem. The reason is that we only update the task-specific part and keep all the shared part among different tasks frozen. So in such situation, we can retain the performance in the scene tasks. And the third nice feature is that hybrid decision transformer are relatively more data efficient. The reason is that the hypernetwork will take additional information resource, which is the trajectory prompt. And then the trajectory prompt will help initialize a good policy, and then which will help reduce the number of interactions used during the exploration phase. We try to evaluate the hybrid decision transformers performance in more challenging generalization problems. In other words, we evaluate in the unseen tasks with different objects and also different reward functions. And specifically, we evaluate hybrid decision transformer in the MetaWorld benchmark, which also have 45 tasks for training and also 5 tasks for testing. And recall those testing tasks will have like new objects and also new reward function. And our main finding is that the hybrid decision transformer can achieve is quite flexible, and it can achieve adaptation through both imitation learning and also reinforcement learning. And when there are expert actions available in the demonstration, we can directly use the supervised learning laws to train the adapter's parameters. And we notice that the hybrid decision transformer, which only updates 0.5% of the whole model parameter, it actually can achieve faster improvement when comparing with the baseline, which is the whole model parameter. And also they achieve a similar asymptotic performance. And when the expert action or actions are not available, we'll have to use the reinforcement learning algorithm. In our case, it's the PPO algorithm to adapt the to change the adapter's parameter. And we notice that the hybridization transformer also performs really well, which have like better asymptotic performance when comparing with the second best baseline. And those observations show that the hybridization transformer could effectively extract the prior knowledge in those provided demonstrations. So that concludes the first part. The main takeaway message in the first part is that we notice that in the classic meta reinforcement learning setting, in-context robot learning actually is quite promising in terms of enabling the adaptation during the pre-training phase. And if we take a step back and look into those two methods, they actually share the same training paradigm, which is one round of training and testing. And although the testing tasks are different from the training ones, we have an underlying assumption, which is the testing tasks are predefined by the human experimenters. However, in the real world, the fact is that it is really hard to predefine the testing tasks. In other words, the robot may have to generalize to like infinite possible number of unseen tasks continually. So the question becomes how to enable the robot agent continually adapting to those unknown tasks. So in the second part, I'm going to introduce. We propose to develop some unsupervised continual reinforcement learning method to automatically discover the relationships between the new task and also other already seen tasks to improve the robot's generalization capability. So this part is heavily motivated by the human's continual learning capability. And we know that we humans keep learning new tasks by interacting with the real world throughout our whole life. And also, humans are really good at identifying similar tasks. For instance, if we know how to put the clothes on the right, we can automatically know how to put the clothes on the left. And basically, we think those tasks are the same task. And mathematically speaking, those tasks are actually geometrically equivalent tasks. And I want to mention that in the robotics domain, many different tasks actually share similar structures. And for instance, take this half-cheetah example again. Like if different tasks or have different disabled joints and also different torsal masses, we know that the disabled joint will have a larger effect on the half-cheetah's resulting dynamics. So if we can treat one task as one set of parameter configuration, we can see that different parameters actually play different roles in terms of affecting the task nature or the task dynamics. So instead of like using one single distribution to represent all the tasks, we propose to use a mixture model, in other words, a hierarchical architecture to model other tasks, to better model the relationships between different tasks, like some tasks may be closer to each other and may be far away from the others. And modeling such task clusters also help improve the generalization capability. And the reason is that it allows positive transfer among different tasks within each cluster and also avoid negative interferences between different clusters. But if we purely rely on human to design such task structures, it may be really hard to scale up. So the question becomes, can we discover those hierarchical task structures on the fly? So in our work, we propose the unsupervised continual reinforcement learning algorithm, which can automatically detect the delineations between the different task clusters and also grow one policy for each cluster. And the whole framework is like this. So if the robot encounters a new task, the robot will first collect some online rollout data capturing the interactions between the robot and also the environment. And then we'll use an unsupervised task clustering mechanism to compare the distance between the raw data and also all the data for the policies already in the policy set. And if the minimum distance is small enough, we will append the rollout data to the corresponding policies data set and then update the policy afterwards. And if the minimum distance is relatively large, we will grow a new policy for the current task and append the data for the new policy and then use the data to update the policy afterwards. And then the selected policy will be used to generate the action to be executed in the current environment. And recall that in our work, we are interested in a set of tasks which may have like equivalent similarities. So here, I first want to introduce a little bit about the equivalent policy because we are going to grow one equivalent policy for each cluster, which have all the equivalent tasks. So we can think about that the equivalent policy is actually a map mapping the action to the mapping the observation to the action. And if we take if we apply a transformation T to the input observation, the equivalent policy will correspondingly transform the action based on another transformation T prime. And then if we can have this nice equation hold, we can say that the policy pi is actually equivalent to the transformation T. And in our setting, we grow a PPO-based policy, and the input to the policy includes the initial frame, the current frame, and also the robust proprioceptive states. And we'll process the input with an invariant feature extractor. And we'll first process the input with the equivalent feature extractor to get the equivalent features. And since the invariance is actually a special case of equivalence, so we can use a group max pooling layer to process the equivalent features to get the invariant features. And then the invariant feature will be used to like generate the to like get the value in the PPO network, and also the invariant features will be used to calculate the distance between the current raw data and also already stored data for different policies. And recall that we have to make the action to be an equivalent, to have some equivalent nature. So we'll use the equivalent features to get the action. And we evaluate our proposed method in the continual learning setting, which have a set of tasks in the table talk manipulation domain. So basically, the agent will continually seeing different group of tasks, including the play slide, button press, draw close, and go reach. We call our method as covers, and we compare covers with like different baselines. And we notice that first covers can achieve really good performance, meaning that the reason is that if we compare covers which use our unsupervised clustering mechanism to discover the task identification, and when compare covers with the ground truth baseline, which directly use the ground truth label to do the clustering, we notice that covers can actually perform quite similar to the Oracle baseline. So it can achieve like near Oracle performance. And we also compare covers with different baselines which doesn't have the unsupervised clustering mechanism, meaning that we only use one network to learn all the like different tasks. And it turns out that the baselines doesn't have steady improvements. So based on those observations, we can say that in the relatively data limited setting, explicitly inferring those task clusters can greatly help improve the overall performance. However, the fact is that in more challenging settings, the task inference can be really inaccurate. And for instance, in our setting, we have to do the unsupervised clustering mechanism, meaning that we have to calculate some posterior distribution. And there may be some inaccurate data, and also the nominal model may also be inaccurate, which will cause inaccuracy in the resulting like posterior distribution. And in some scenarios, especially in the human-robot interaction scenario, those inaccurate task inference may lead to like catastrophic failures, which we definitely want to avoid. So the question is, can we like robustly handle those inaccurate task inference about the task clusters? So in our work, in our another work, we first propose the robustness notion that is suitable for the hierarchical model. And we noticed that the hierarchical model not only can help improve the general like generalization capability, it can also help balance the robustness and also the average performance. And first, the robustness formulation we proposed is called the group distributional robustness formulation. So basically, in this formulation, the agent is assuming that the worst possible belief over the mixture is going to happen in the future. And we can write out this minimization, we can write out this equation and see that there's a minimization over the belief over Z, and the belief is sampled from ambiguity set C. And definitely there are other robustness formulations like the distributional robustness formulation, which have a minimization over the beliefs over task configurations instead of the mixtures. And there are also other formulations like the group robustness formulation, which directly remove the distribution in the equation and directly finding the worst possible mixture within the mixture set. And then there's also this robustness formulation, which is directly finding the worst possible case over the task configuration. And we notice that we can rigorously prove that the group distributional robustness formulation is kind of better than the other robustness formulations regarding the value of the optimal policy. And the key intuition is that the mixture model basically can serve as a regularization because it regularizes the projected ambiguity set, measuring the power of the adversarial nature, which is doing the minimization. And so in this situation, it can help generate less conservative policy and achieve a better balance between the robustness and also the average performance. And that concludes the second part, which is when there is only reward available in the unseen task, we propose to improve the generalization capability by measuring the relationship between the new task and also already seen task. And we notice that discovering those task structures help improve generalization a lot. So in the second part, sorry.
Meng, do you mind if I ask a question?
Yeah.
Yeah, because for the last slide you were showing was a difference between being able to maximize rewards and coverage instead. And I'd be interested to get some of your thoughts on, for the future for robotics applications and applied world things, do you think we should be maximizing reward or focusing more on robustness and coverage?
Oh, I see. That is a good question. So I think so. From my point of view, I think only maximizing the reward is not really sufficient because in the real world, in a lot of situations, we have to consider the robustness and also the safety. Like in the human-robot interaction scenario, and also in some tabletop manipulation, there may be some really fragile material, and we don't want the robot to break any glasses. So in such situation, we have to strike a really good balance between the average performance measuring the maybe can be measured by maximizing the rewards and also the robustness and also the safety measures. I think how to balance them is kind of a really hard problem, and it's definitely the way we need to go.
Okay, great. Yeah.
Mm-hmm.
Any other questions?
Yeah, thanks. Yeah.
Right, go ahead. Or continue.
Yeah. Thanks. So in the third part, we are heavily motivated by the recent success of the large foundation models. And in this work, we are hoping the robot agent to solve some even challenging problem, such as the long horizon tasks. And so in this work, we propose a robot tool system, which for the first time enables the creative robot tool use behaviors to solve multiple real-world physical puzzles in a kind of zero-shot manner. So first, I want to introduce what is the creative robot tool use behavior. I want to take this quadrupedal robot as the example. So basically, in this situation, the robot is being asked to climb onto the sofa. However, we know that the robot can only climb up onto a stage which is lower than 0.2 meters. We know that this robot is not really powerful. However, the sofa is of height 0.4 meters. So we know that if the robot is going to directly use its climbing skill to climb onto the sofa, it's not really possible. But as humans, we know that there are other objects in the scene, like there are two like huge black boxes. And if the robot learns to push those boxes and align those boxes to make stairs and then use the stairs to walk up onto the sofa, we know that in this situation, the task is actually feasible. So basically, this is one great example of the creative tool use behavior we are interested in. And regardlessly speaking, it's basically referring to the behaviors of agents which can use tools beyond their standard functionalities. And we see that a lot of animals, they have such creative tool use behavior, such as crows and apes. They can use rocks and sticks to help them get food. However, such creative tool use behavior require like holistic intelligence, and it's a really hard task. Basically, it requires the understanding of physical concepts such as the weights, the size, and also even the materials of different objects. And then the agent, we also have to, like, based on those physical concepts, as an agent, we also have to reason the activated constraints, which may be related to both the embodiment constraints and also the environment information. And then based on those physical concepts and the activated constraints, the agent then needs to like generate a feasible plan to solve the current task. And the existing literature are trying to approach such problem based on task and motion planning. And although we see a lot of like exciting results based on those temp methods, however, temp methods will have like some limitations. The first one is that we may require some like planning mechanism, like doing some large sampling, which will cause a lot of like computational will resume a lot of like computation resource. And then like we need to predefine some syntax, which may also limit the generalization capability. So in our work, we are motivated to leverage on the large prior knowledge in the large language models to solve those physical puzzles and enable the robot's creative tool use behavior. So the input of our robot tool system include both the human provided instruction and also a text-based description of the current environment, including the objects and also the object's positions, sizes, and also shapes. And we'll also provide the robot tool system with the constraints the robot needs to follow. And then the robot tool system will output the executable code, which can be executed in both the simulation and in the real world. So recall that we mentioned three challenges in enabling the creative tool use behavior. So to tackle those challenges one by one, we proposed the robot tool system containing like 4 different like language models. And to understand the physical concept and reasoning the activated constraints, we'll use an analyzer which is basically one language model to output the key feature that will affect the feasibility of the current task. And then we'll use the calculator to kind of process all the numerical numbers. And to generate the executable code, we'll first use one language model as a planner to generate the step-by-step text-based plan. And then we'll use the coder to process the text-based plan to the executable code. So with the robot tool system, we doesn't really need to solve any optimization loops or do large amount of sampling and search. So in overall, the robot tool system is more efficient. And also because we have a calculator to process all the numerical numbers, so our method has like stronger physical grounding capability. And also we can leverage on the goal condition policies. And also, I want to provide another example to like better illustrate how the robot tool system works. Basically, in this example, the robot arm is asked to push the button. However, the button is originally out of the robot's workspace. So we will first use an analyzer to process the input, including the task instruction and also the text-based description of the current environment. And in this situation, we know that the key feature is actually the position of the button. And we notice that the analyzer can actually successfully output the key feature, which is the X position of the button. And also it can relate the key feature with the possible violated constraints that the robot needs to follow. And then the output of the analyzer and also the original input will serve as the input to the planner, and the planner will generate the step-by-step text-based plan. And then we'll use the calculator to fill in the numerical numbers, which are actually the 3D target poses for each skill the planner is going to invoke. And then we will use the coder to transform those text-based plan to get us a Python script. We notice that in the Python script, the robot is going to invoke some like different functions, which are actually different skills of the robots, including the move to position skill, open gripper skill, and also the close gripper skill. And here I want to mention that in our situation, the skills of the robot are actually not related to the tasks. So basically, they are task agnostic, and which can also help improve the generalization capability. And in this situation, the robot tool system will generate a plan, which is like notice that there are like different magnetic cubes in the scenario. So it will like first grasp one magnetic cube and then like attach different magnetic cubes one by one to construct a longer stick. And then we'll use this longer stick to push the button, which is originally out of the robot's workspace. And to systematically evaluate the robot tool system's creative tool use capability, we propose like 6 different tasks across 2 different morphologies. And basically, we want to test 3 types of tool use behavior, including tool selection, sequential tool use, and tool manufacturing. And for the tool selection part, I want to provide another example. And in this task, the robot is going to grasp the milk carton. However, the milk carton is also originally out of the robot's workspace. But the robot tool system can generate a plan, which is the robot will first need to select the correct tool among different objects. And in our situation, the correct tool is the hammer. And then it can use the hammer to grasp the milk carton and drag the milk carton to make it within the robot's workspace and then grasp the milk carton. And previously, I have already seen 2 examples, including the climbing onto the sofa, which is one type of sequential tool use behavior because the robot is going to use those boxes one by one. And then the pushing button example is one like it actually shows the tool manufacturing behavior because we are going to construct a longer stick based on those smaller magnetic cubes. And through the numerical evaluation, we noticed that the robot tool system can indeed generate a lot of like creative tool use behaviors. And we test the robot tool system's performance in both simulation and also in the real world. And we noticed that in the real world, the success rate is around 77%. But there is indeed a slight performance drop between the simulation and the real world. The reason is that when executing the code in the real world, there are some additional like perception and execution errors. We also did kind of extensive ablation study to show the effect of different modules in the robot tool system, and we noticed that especially the analyzer can help reduce a lot of the tool use errors, and also the calculator can help reduce a lot of the numerical errors. So those results actually show that different modules in the robot tool system help improve the overall success rate. So that concludes the 3rd part. Basically, is using large foundation models to enhance the robot's capabilities. But the situation is that we have to do careful system design to make sure that the part knowledge in the large foundation model is successfully conveyed to the robot. Yeah, so that actually concludes my talk. So last, I want to thank all my collaborators, and I'm also happy to take additional questions.
All right. Thank you, Mengdi.
Thank you.
Question?
Yeah, I had a question on this last work. Sorry if I missed it, but how do you get the language description of the scenes?
Yeah, that's a good question. Sorry, I'll omit that. So basically, we have a template. Basically, it's a hand-designed template saying that there the template will contain first describing the current scenario, which is like if we are going to run the robot tool system in the robot arm platform, we'll first describe that you're a robot arm, you have a like fixed base, and the task is something, and the task is actually provided by the human like experimenter. And then we'll use the external visual module, which is powered by the OWL-VIT, to get the bounding boxes of different objects. And then we will fill in those numerical numbers to the corresponding slot, describing the different objects, positions, sizes, and also the general shapes. So basically, right now we are using a hand-designed, crafted text-based template.
Great, thank you.
Mm-hmm.
Other questions? I mean, I've got one that's a bit more high level here because there's a handful of papers and they're kind of going two directions lately. There's the ones that are like the tool paper that you've done here that work great, and they combine like some pre-trained models with some skill libraries and being able to control things. And then there's the group of directions that are kind of like end-to-end foundational models for being able to control robot systems.
Mm-hmm.
So if I could get like some of your thoughts on like which one of these sets of methods do you think will be better for like doing large scale and generalist robotics problems?
I see. Yeah. So basically, I think in general, in the future, the robot system can be also a hierarchical system, meaning that we have some like high-level planner to solve those like long horizon tasks, and there may also be some low-level controller which powered by the robot foundation models that can directly output the low-level actions of different robots. So in general, I think it would be great to leverage on the large foundation model from other domain, like from the NLP domain or from the computer vision domain, because we can leverage on the vision language model to, instead of like in our robot tool system, we directly use the handcrafted text-based input. Instead we can directly use the vision language model to process images and then generate the plan. But I definitely feel that in the future we should have this hierarchical system, because it's not really like reliable to have one model to solve this like really long horizon task. It may be really challenging, and it's better to have kind of separate the high level plan and also the low level control part to help improve the overall performance and also make the system more interpretable.
Okay, thank you. Other questions? People online are also welcome to ask questions. All right, I think we can wrap up there for today. I know you've got a few other people to chat to later.
Yeah.
But I think that's it. Thank you very much, Mengdi.
Great. Yeah, thanks for having me. Yeah. Thank you.